Virtually all biochemical reactions are catalyzed by enzymes, each enzyme usually being quite specific for its purpose and catalyzing the reaction with the utmost of efficiency. So you'll appreciate it's important to understand how enzymes work, the mechanism of enzyme action. In the last program, we examined the imidazole-catalyzed hydrolysis of paranitrophenol acetate, and you'll remember that one of the reasons why we chose this catalyst was because the imidazole group turns up in the active site of a large number of enzymes that catalyze hydrolysis. So let's review what we found out there about catalysis using smaller molecules, because almost certainly similar principles apply to enzyme catalysis. Under the same experimental conditions, the hydrolysis of paranitrophenol acetate to acetic acid and paranitrophenol goes faster in the presence of N-methylimidazole than in its absence. And this catalysis is reflected in the experimental rate equation for this reaction, which includes a term for the N-methylimidazole concentration. The role of the catalyst is to provide a speedier route between reactant and products, and this is the mechanism we established. Notice the role of the N-methylimidazole. It's involved in the bond making and breaking processes and is a constituent of the intermediate. But as we saw, the concentration of this intermediate is very small, and thus since N-methylimidazole, which is consumed in the first step, is regenerated in the second, the overall concentration of N-methylimidazole does not change. Put another way, it is not consumed during the reaction, in accord with the definition of a catalyst. Now, an obvious question is, why does the catalyzed reaction go faster than the uncatalyzed process? Well, the catalyst increases the rate, usually by providing the reaction with an alternative pathway involving a lower overall activation energy. We can show this by taking our analysis a stage further and determining the activation energy for this type of reaction using the Arrhenius equation. If we take logs of the Arrhenius equation, we obtain the equation of a straight line. So if we determine the rate constant at a range of different temperatures, we could plot Kr dashed against reciprocal temperature. This should give a straight line of slope equal to the negative of the activation energy, Ba, divided by 2.303 R. Such a plot is indeed linear, has a negative slope, and for imidazole, gives a value of the activation energy of about 35 kilojoules per mole. The activation energy for the uncatalyzed process has been found to be at least 87 kilojoules per mole. Further analysis shows that the difference in the A factor between the catalyzed and uncatalyzed process does not lead to an increase in the rate for the catalyzed reaction. If anything, it causes a decrease. So clearly, the main reason why the imidazole catalyzed reaction is so much faster is because the catalyst does indeed provide a mechanism involving a much lower overall activation energy. Having reviewed catalysis using relatively simple molecules, let's now move up a scale and examine enzyme catalysis. Like any other mechanism, the mechanism of enzyme action is ultimately defined when all the intermediates and complexes along the reaction pathway have been characterized, and the various rate constants for their interconversion have been measured. The role of the kineticist in this is to determine the number and sequence of these intermediates, and to measure the rate constants. The next, and perhaps more difficult task, is to establish the chemical nature of these intermediates. We're going to concentrate on the kinetic studies, but despite this emphasis, you should always remember the primary importance of structural analysis. Indeed, the structure of the enzyme that we're about to study clearly shows the size of the problem which faces the structural chemist. This is alpha-chymotrypsin, one of a group of so-called proteolytic protein-splitting enzymes. It occurs in the pancreas of most mammals and catalyzes amide hydrolysis as part of the process in which the proteins are digested. The enzyme has a molecular weight of around 25,000, and its structure has been painstakingly worked out using X-ray crystallography. It's roughly spherical, extremely compact, and rather complex. The active site is here. The substrate, that's the reactant molecule with which the enzyme combines, binds in this pocket, which provides an ideal environment for reaction. This environment is provided by arranging the various groups of the amino acid residues in their optimum positions. Sure enough, one of these groups in the active site is imidazole, which is part of the amino acid histidine. Chymotrypsin's biochemical action is to split proteins by hydrolysis of the internal amide peptide bonds. But it will also catalyze the hydrolysis of a number of simpler model substrates, amides, and esters such as paranitrophenol acetate. The reaction of such synthetic substrates has been of great value in establishing the mode of action of chymotrypsin. So let's now examine how we can determine the mechanism of enzyme catalysis using, as our model reaction, the hydrolysis of paranitrophenol acetate, since the progress of the reaction is easy to monitor using UV spectroscopy. As in the last program, I start by proposing a possible chemical rate equation. Then determine experimentally the partial order with respect to each species. Again, I've not included a term for water because it's a solvent. We start the experiment by examining the kinetics of this reaction when the concentration of the substrate is greater than that of the enzyme, a steady-state study. Under these conditions, the reaction exhibits time-independent stoichiometry. As before, the variation in the concentration of the product with time can be established by monitoring the absorbance at 400 nanometers due to the product paranitrophenolate ion. Then, using the Beer-Lambert law, the absorbance can be converted into concentration. For a number of reasons, such as the instability of the enzyme, it's not possible to use a whole reaction profile of an enzyme-catalyzed reaction when carrying out a kinetic study. So how do we get around this problem? Well, one way is just to study the beginning of the reaction, which doesn't suffer from these complications. We measure the initial rate, and by establishing how it varies as a function of the concentration of one particular species, we can measure the partial order with respect to that species. Usually, to obtain the initial rate, we establish how the absorbance, and hence the concentration, varies with time, and then draw a tangent to the curve at the origin. But if only the initial 10 or so % is measured, the curve is practically a straight line anyway. So it's easy to determine the initial rate for various concentrations of paranitrophenol acetate and chymotrypsin. Having established how the initial rate varies as a function of the concentration of each of the species in the chemical rate equation, I can now use the differential method to determine the partial orders. We start by taking logs of the proposed rate equation. This relates the log of the initial rate to the log of the constant Kr and those of two variables, the initial concentrations of paranitrophenol acetate and chymotrypsin. If the initial concentration of the substrate, paranitrophenol acetate, is kept constant, the expression reduces to that of a straight line. So if we vary the concentration of the enzyme, then plot the logarithm of the initial rates against the logarithm of the initial concentration of chymotrypsin, we should get a straight line of slope beta. Such a plot is indeed linear, with a gradient of about 1. Clearly, the reaction is first order in chymotrypsin. If we hold the initial concentration of chymotrypsin constant, leaving the paranitrophenol acetate as a variable, then we again get the equation for a straight line. Well, what do we get now if we plot the log of the initial rate against the log of the concentration of substrate? It's not linear, as we would expect. It's a curve. So we can't define the partial order with respect to the substrate. Clearly, our experimental rate equation is not as simple as we first thought. Such behavior is frequently found for enzymes, and further analysis often reveals that they follow Michaelis-Menten kinetics. That is, the chemical rate equation has this form. We can test whether chymotrypsin follows Michaelis-Menten kinetics using this rearranged form of the chemical rate equation. If the concentration of the enzyme is kept constant, a plot of 1 over the initial rate against 1 over the concentration of paranitrophenol acetate should be a straight line. This is known as a Line-Weaver-Burke plot, and such a plot using data for chymotrypsin is indeed a straight line, confirming that this enzyme does follow Michaelis-Menten kinetics. Whilst a number of mechanisms have been proposed which are in accord with Michaelis-Menten kinetics, the mechanism is usually assumed to be a simple two-step process involving one intermediate. The enzyme and the substrate react to give a substrate-enzyme complex, sometimes called a Michaelis complex, which decomposes to regenerate the free enzyme and the product. This is the simplest two-step mechanism involving only one intermediate for the chymotrypsin catalyzed hydrolysis of paranitrophenol acetate. Recently, it's become increasingly clear that although a wide variety of enzymes follow Michaelis-Menten kinetics, the actual mechanism is frequently more complicated than this simple two-step process which we propose from our steady-state studies. For a considerable number of reactions, there is evidence for a second intermediate formed after the Michaelis complex. But the rates of these subsequent steps are very fast, so the application of the steady-state assumption to these reactive intermediates generates a chemical rate equation which has exactly the same form as the Michaelis-Menten equation. Since the kinetic form is the same irrespective of the number of intermediates, steady-state studies can tell us nothing about the number of intermediates. Sometimes this information can be obtained by examining how the system approaches the steady state. But because the steady state is obtained very quickly, we can't use the experimental techniques that we've used in our previous studies. By the time we've mixed the reagents and placed a cell in the spectrophotometer, the crucial pre-steady state period will have passed. To study this region, we had to use a new instrument, known as a stopped flow spectrophotometer. Let's first look at the spectrometer aspect of the apparatus. There's a light source, which passes through a grating so that we can select a particular wavelength. Usually in the visible to ultraviolet. And to detect the absorbance of paranitrophenolate ion, light at a wavelength of 400 nanometers is transmitted through a fiber optic to a reaction cell housed inside a thermostat. The light leaving the cell is again fed out through a fiber optic to a photomultiplier which measures the absorbance, and its signal is sampled and recorded by a computer 500 times over a short period, then stored on a magnetic disk. The paranitrophenol acetate and the chymotrypsin solutions are charged into two reservoirs which feed two ram-driven syringes. When these are compressed, they will express equal volumes of each solution into a mixing chamber, which allows efficient mixing of the reactants in a fraction of a millisecond. As I purge bubbles from the system, you can get some impression of how the mixing takes place. As the drive syringes are depressed, the solution leaving the cell enters a third syringe. When its plunger hits a backstop, the flow is stopped, and a microswitch closed to set the computer recording the absorbance time data. Well, now we are ready to perform our pre-steady state study using a 10-fold excess of paranitrophenol acetate over the enzyme concentration. Now all I have to do is to recall the data, and since the computer is already programmed with the parameters of the Beer-Lambert law, I can display a plot of the variation in the concentration of paranitrophenolate ion with time. When the paranitrophenyl acetate is mixed with chymotrypsin, the release of paranitrophenolate anion occurs in two phases: a rapid burst followed by a relatively slow steady region. By extrapolating the steady state region back to time 0, we can establish that the amplitude of this burst corresponds to the concentration of enzyme in the system. That is, this initial burst liberates 1 mole of product for each mole of enzyme. These results are best interpreted as implying that there is a rapid formation of an intermediate accompanied by the liberation of paranitrophenolate ion in one step, followed by the slow breakdown of this intermediate to give the other product, acetic acid and free chymotrypsin. This can quickly react with more paranitrophenyl acetate and thus continue the catalytic cycle, which further increases the concentration of paranitrophenolate ion. Because this second step is slow, the steady state production of paranitrophenolate anion will also be slow. The interesting point is that this new intermediate is not the Michaelis complex, whose presence we determined from our steady state studies. Although we haven't got time to go into details now, the rate of formation of this new intermediate does not correspond to that expected for the Michaelis complex. So there must be two intermediates, and this is the most likely mechanism. The enzyme and the substrate react very quickly to give the Michaelis complex. This is followed by the release of paranitrophenolate ion and the formation of a second intermediate called an acyl enzyme intermediate. This corresponds to the burst. Finally, the acyl enzyme intermediate breaks down, yielding free chymotrypsin and acetic acid. This latter step is rate limiting and controls the overall rate of reaction in the steady state. Further evidence in support of this mechanism is obtained if another substrate other than paranitrophenyl acetate is employed. This new substrate is fuaryl acryloyl L-tyrosine ethyl ester. But don't worry too much about its structure. This compound absorbs light in the region of 330 nanometers, but notice that in this case it is the acid or acyl part of the ester grouping that absorbs the light. If we carry out a transient kinetic study, that is when the concentration of the enzyme is equal to or in excess of that of the substrate, various processes can be observed using the stop flow technique. This shows the change in absorbance due to the acyl part of the substrate molecule as it passes through a single turn of the catalytic cycle. On mixing, there is a very fast change in the absorbance, the rate constant of which is beyond the timescale of the stopped flow. This corresponds to the formation of the Michaelis complex in the first step. The absorbance then increases to reach a maximum. This corresponds to the second step, when the acyl enzyme is produced. Notice that this still occurs very quickly. This is then followed by a slow decrease in absorbance as the intermediate is hydrolyzed to give free chymotrypsin and the corresponding carboxylic acid. Now we've virtually completed the kineticist job. We've established the number of intermediates. So let's look at some aspects of the structural analysis of the intermediates. The structure of this acyl enzyme has been investigated by a number of techniques. As we've seen in the last experiments, the concentration of the acyl enzyme intermediate can reach substantial proportions during the reaction. If the reaction mixture is rapidly acidified to pH 4, the intermediate becomes stable enough to be studied directly. By using carbon-14 labelled paranitrophenyl acetate, it's possible to generate a radioactive acyl enzyme. If this is carefully degraded, all the radioactivity is found to be associated with one amino acid, a serine amino acid, which is numbered the 195th in the sequence of amino acids in chymotrypsin. This contains an OH group, which reacts with the paranitrophenyl acetate in the second step to form the paranitrophenolate anion and the acyl enzyme. So the structure of our acyl enzyme intermediate is an ester of a serine amino acid. And what's more, serine 195 is the only one of the 28 serine groupings in the enzyme to do this, confirming that this is the region of the active site. So, our structural studies have identified the special role of serine 195 in the catalysis. But there are still unanswered questions. What are the functional roles of the other amino acid side chains in the active site? For example, it's important to have an imidazole group in the active site, since, if this is modified in some way, the enzyme loses its activity. And judging from our previous studies with imidazole, we would have expected to have seen an acyl imidazole type intermediate. But clearly we don't. So what is the role of imidazole? Well, the answers to these questions are given in the broadcast notes.